This is lecture 18. In last lecture, we have discussed what is root locus. Today, we will show some basic rules for sketching that root locus. So here, I'll be pointing out 7 rules. By applying those rules, you can easily draw that root locus whenever one open loop transfer function is given to you. So the first rule is that number of branches. So number of branches. As we know, whenever we vary that gain, how the closed loop poles will be varying, its representation, graphical representation is known as root locus. So the number of branches in one root locus is equal to the number of closed loop poles. Whenever one open loop transfer function is given to you, then just by looking at that characteristic equation, you can easily find that how many closed loop poles are there. So the number of branches, so the number of branches of the root locus equals to the number of closed loop poles. This is obvious. So we'll understand this particular fact from one example. So let us see. Say suppose you have one characteristic equation here, that k is that gain which will be varying, and you have that open loop transfer function, or you can say that loop transfer function, that is g of s h of s, that loop transfer function. So this is equal to 0. So from here we can see that the number of closed loop poles, so that means if you just multiply this numerator and denominator by s plus 3 into s plus 4, so here you have, that means the characteristic equation that you have, that is s plus 3 into s plus 4 equal to that k. So that means that is that varying parameter 2 equal to 0. So here you can see the number of closed loop poles. So the number of closed loop poles equal to 2, because you can see if you just multiply this one, the degree would be 2. So the maximum degree of that characteristic equation is 2. So the number of branches in a loop locus is equal to the number of closed loop poles 2. So in this particular case, the number of branches equal to 2. So now another interesting point we can understand from here, that means whenever this k varies, so we have considered that negative feedback case here, that means k will be varying in positive side 0 to infinity. So now the question is, whenever k is equal to 0, what would be the locations of that closed loop poles, and when k equal to infinity, what would be that location? So from this particular characteristic equation, we can see that open loop poles, so two open loop poles are there. One is at -3 and another one is at -4. And 0, there is one finite 0, that is -2, and another 0 is there, that is at infinity. So now these are the open loop poles and zeros. So mind that these are the open loop poles. But root locus is the graphical representation of closed loop poles whenever that K is varying. So here we are interested in to see what would be the location of the closed loop poles whenever K equal to 0 and K equal to infinity, because this K is varying from 0 to infinity. So if you just look at that characteristic equation, so whenever K equal to 0, whenever K equal to 0, then you can see that this term would be equal to 0. So you have s plus 3 into s plus 4 equal to 0. So that means s equal to minus 3 and s equal to minus 4. These are the two solutions. These are the two closed loop poles when K equal to 0. So that means here we can write that when K equal to 0, s equal to minus 3, s equal to minus 3 and s equal to minus 4 are two roots of the characteristic equation. That means these are the two poles of the closed loop system. So it is very interesting, when K equal to 0, actually that root locus starts from the open loop poles. Now let us see whenever K equal to infinity. So we can represent this particular characteristic equation. So this characteristic equation in this particular form that I am going to write. So if we divide by K, that is 1 by K equal to s plus 2 divided by s plus 3 to s plus 4 equal to 0. So now we can divide this particular term, numerator and denominator, by s square. So if we divide that one, what we get, that is 1 by s plus 2 by s square, and here we have 1 by s plus 3 by s square, and here we have 1 by s and 4 by s square equal to 0. So now when K equal to infinity, K equal to infinity, K tends to infinity, so this particular term would be equal to 0. And now we can see that. So that means this term would be equal to 0. So now you can see that what would be the value of s whenever this particular equation is satisfied, characteristic equation, that is s equal to minus 2. So what is that s equal to minus 2? That is actually that open loop 0. So it is very interesting that whenever K tends to infinity, that root locus, that particular branch, tends to or approaches to the open loop 0. Again, repeating, when K equal to 0, so then you can see that this characteristic equation is satisfied at s equal to minus 3 and s equal to minus 4. So that s equal to minus 3 and minus 4, they are actually the open loop poles. So when K equal to 0, the open loop poles are actually the closed loop poles. Now when K tends to infinity, we have seen that means this term. So this equation we get just rewriting this characteristic equation. Now we can see that the first term is coming equal to 0 and this term should be equal to 0, so that this particular equation would be satisfied. So now when K tends to infinity, at s equal to minus 2, this characteristic equation is satisfied. And what is that minus 2? That minus 2 is the open loop 0. Another interesting thing is, if we look at this particular expression, so this expression we get just rewriting the characteristic equation. Now, if s equal to infinity, then you can see that this term, again it would be equal to 0, and this is 0, and you can see that at s equal to infinity, this particular, so here I think there is a mistake here, so that would be 1, because we are dividing by s square, so it would be 3 by s 1 plus 4 by s, otherwise it would be 0 by 0, so that does not make sense. So here whenever s tends to infinity, then we can see that this term is coming as 0, and here this is equal to 0 and this is equal to 0, so that is 0 by 1. So that means this particular equation, that is the characteristic equation, is satisfied whenever s tends to infinity. So as I have pointed out here, if you look at that loop transfer function, it has one finite 0 at minus 2, but there is another 0 which is that infinite 0, infinity. So when k tends to infinity, then that root locus approaches to the zeros of the open loop plant, because here the two zeros are there. One is that finite 0 minus 2, and another one is infinite 0 infinity. And from this particular expression we have shown that when k is tending to infinity, then that when k tends to infinity, then s equal to minus 2 is a root of characteristic equation. That means that is that closed loop poles. So at k equal to infinity, zeros of the open loop system would be the poles of the closed loop system. So k tends to infinity, s equal to infinity is a root of characteristic equation. So here in the first rule, what we have seen, the number of branches is equal to the number of closed loop poles, and here we have seen that when k is varying from 0 to infinity, at k equal to 0, that root locus is at the open loop pole location, and when k tends to infinity, the root locus is at the open loop 0 location. And at k equal to 0, that open loop pole is equal to that closed loop poles, and when k equal to infinity or k tends to infinity, that open loop 0 is actually the closed loop poles. So this is very interesting result. And now the second thing is the symmetry. The second rule is symmetry. So this is very easy to understand. The reason is, what we have discussed so far, we have seen that closed loop characteristic equation, that polynomial is with all real coefficient. So since it has all real coefficients, then the roots of that polynomial, it would be either real number, or if it is complex, that would be complex conjugate. That means with respect to the real axis, all the roots would be symmetric. So that means as the root locus is the graphical representation of all closed loop poles, and as the poles locations are symmetric to the real axis, so then closed root locus is symmetric with respect to the real axis. So that means the root locus is symmetrical about the real axis So real axis, because whenever we draw root locus, we draw it in S-plane. It has that real axis and imaginary axis. So since the polynomial, so polynomial means here the characteristic polynomial is a real coefficient polynomial. So root locus, whenever we sketch root locus, so this thing we should keep in our mind. That means it is always symmetric with respect to that real axis. So let us see what is the third rule. That is that real axis segment. So real axis segment means, so if you just consider that S plane, say this is that S plane, so this is sigma and this is j omega, this is that S plane. So now we have seen from that pole zero plot, whenever one loop transfer function is given, suppose in this case have pole here, another pole here, so those poles are actually that open loop poles. So one pole here, and suppose you have 1 0 here. So now the point is, whenever k is varied from 0 to infinity, then we have just discussed now that root locus will start from when k equal to 0. So root locus will start from those pole locations, and those poles are actually that open loop poles. And one of the branch will end up here at the 0 location. The reason is when k tends to infinity, that closed loop, one of the closed loop poles will be tending to that 0th location, and the other two branches will be going to infinity, because that we have discussed here. So in this particular case, as we have taken only one finite 0, so one of the branches will end up at this particular finite 0th location. The other two branches will go to infinity. But that is actually not our objective here. Our objective is, whenever that root locus will start from this particular open loop poles location that we have discussed. Now the question is whether, say suppose for this particular pole, so it starts from this point, then it may go along this direction, or it may go along this direction, or it may simply go in other directions. So now the question is the real axis segment. The real axis segment means whenever that poles, closed loop poles or root locus will be moving on the real axis, which portion of the real axis will be the part of root locus. So let us discuss it in detail, so then I think it would be clear. So here we have say two open loop poles, and let us see. So suppose you have one pole here, another pole here, or you have 1 0 here, another 0 here. So these all are the complex conjugate poles and zeros. So now if this particular portion of the real axis belongs to the root locus, that means when k is varied from 0 to infinity, that closed loop poles will be here in this particular branch. So then our objective is, which portion of the or which segment of the real axis would belong to the root locus. So now if we just consider a point here, or if we consider a point here, then let us see what would be the contribution of complex conjugate poles and zeros. Contribution of complex conjugate poles zeros means what? We have seen that angle contribution, that means a particular point would satisfy the characteristic equation whenever g of s, h of s would be equal to 2k plus 1, 180 degree. That thing we have seen in last lecture. So this particular condition needs to be satisfied. So here if we take that k equal to 0, so that means 180 degree. So and also we have discussed whenever that angle condition is satisfied, then always we can find one gain for which that k would be equal to 1 by that mode of gs of hs. So that thing we have discussed in last lecture. So now we are interested in to see, that means what would be the angle contribution, what would be the angle contribution whenever we have that complex conjugate poles and zeros. So let us see. So this is one complex conjugate poles, and suppose we have taken this particular point. And if we say that, so this is that s equal to s1, this is that point in the root locus, and that is on the real axis. Then we can see that this is that 0 reference line. So this is that angle contribution, and here you can see that this is that contribution, because these are the two vectors. So what is the contribution? So this angle plus this angle would be equal to 360 or 0 degree, and here you can see that means what would be the contribution from a complex conjugate 0. You can see here that this is that angle, and here this is that angle. So that means this angle and that angle, again that is 360 degree. So if you take any point on the real axis, the contribution of the angle contribution of the complex conjugate poles or 0, it would be always 360 degree or 0 degree. So that is very interesting and important concept in root locus. The resultant contribution of complex pole and or 0, that means if you take pole or 0 or pole and 0, is always it is 360 degree or 0 degree. So that means you can say that the pole, that means if you have complex conjugate poles or zeros, and if you take any point on the real axis, the contribution due to that complex conjugate poles and zeros, it would be 0 degree. So that means if you have complex conjugate poles or zeros like this and that, so what you can have? You can have 0 degree here. So now, but one particular point on the real axis, suppose this point, we have considered this particular point, so s equal to s1 would be the solution, would be the root of the characteristic equation if it satisfies this particular condition, angle condition. But we have seen that if it has complex conjugate poles or zeros, its contribution is 0 degree. So we need actually 180 degree to satisfy it. So let us see what happens. So suppose you are here. So if you are here, so then you can see that for this particular pole, its contribution is 0. For particular pole, its contribution is 0. Why I am telling 0? Because if you just draw this vector, then this is along that 0 degree line. For this one is also 0. For this one is also for 0. For this one is also for 0. So that means here you are getting 0 degree equal to 180. That means if you take any point in this particular segment, that means from this particular pole location to plus infinity, always you will be having 0 degree here. That means it does not satisfy this equation. So this particular segment does not belong to root locus. So let us see what happens if we consider from this particular segment to this segment. So if you take this particular point here, due to complex conjugate poles is zeros, it is coming 0. Now, if you take any point inside this range, then what you can see that, suppose this is that point, then for this particular pole, you have contribution 180 degree. For this one, you have 0 degree. So that means, and for this one, this is 0, and for this one, this is 0. So that means if you take any point inside this particular branch, that means if any point on this particular real segment here, then you can see that it is satisfying this particular angle condition. That means for this particular pole, it is contributing 180 degree, and the other two poles, this pole, that pole, and this 0, they are contributing 0 degree. So we have seen that from here to here, this particular portion belongs to the root locus. The reason is it satisfies this angle condition. So let us see here. So now if we just consider this particular segment from here, from this particular pole location to this location, then what happens? Suppose you have a point here. So if you have a point here, then you can see that for this particular pole, it is 180 degree, and for this pole, again it is 180 degree. So it becomes 360 degree. And for this one, it is coming 0 degree, and for this one, it is coming 0 degree. So that is 360 degree equal to 180 degree. That means it does not satisfy it. Similarly, if you look at here in this particular segment, then you can see that if there is a point here, then for this one, this is 180 degree. For this one, this is 0 degree. And for this one, it is 180 degree. That means 360 degree plus for this one, it is 180 degree. That means it satisfies this particular condition. So interestingly, we have seen that this particular segment again belongs to the root locus. But if you look at here, this particular segment, that means from this location to minus infinity, you will see that this particular portion again does not belong to the root locus because it does not satisfy the angle condition. So what interesting thing we have seen, how to know that which portion of the real axis belongs to the root locus. Mathematically, the portion that satisfies this angle criteria, that belongs to the root locus. But here we have seen that this is one pole location, this is another pole location, this is another pole location, this is the 0 location. So if you start counting from here, you can see that this is 1, this is 2, this is 3, this is 4. I have started counting from this side. Now, if you are here, and if you look on the right, how many poles or zeros are there? 1. That means odd number. If you come here, so how many poles and zeros are here on the right hand side? 2. So even number. If you come here, how many poles and zeros are there? 3. That means odd number. So that means the portion of that real axis would belong to the root locus if you look to that right, and if the number of pole and zeros is that odd number, then only that portion would belong to the root locus. So let us write And then I think you understand this very important thing that on the real axis, for k greater than 0, because we are discussing that positive k, the root locus exists. So again, it is on the real axis. We are actually discussing which segment of the real axis belongs to the root locus. That means which segment of the real axis satisfies this angle criteria. So that thing we have discussed in detail here. Exists to the left of an odd to the left of an odd number of real axis. So that means if you look at to your right, finite open loop poles and or finite open loop zeros. So this is very important in root locus. So here two things you can see. This is that finite. So on the real axis for k greater than 0, the root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. So here you can see that you may ask, if we have some complex conjugate poles and zeros, then what to do? So first of all, we have discussed, if you have complex conjugate poles and zeros, its contribution is 0 whenever you are on the real axis. So which portion of the real axis belongs to that root locus? In that case, complex conjugate pole zeros contribution is 0 there. So now here we have seen that you have a pole here, you have another pole here, you have here another pole and 1 0. So these all are finite poles and zeros. According to this statement, the root locus exists to the left of an odd number. So this is 1. So left to this odd number means this portion. Now if you come here, now you can see on the right you have two numbers. So that is not odd. So that means this portion does not belongs to that root locus. But if you come here, you can see that this particular portion again belongs to the root locus, because if you are here, then you can see that on the right you have 3 number of poles, but if you are here, you can see that you have 4 number of poles and zeros. So in this particular example, so this particular portion and this particular portion belong to the root locus. So this is very important. This rule 3 is very important. So now let us see the fourth rule, that is centroid and asymptotes. What is that, centroid and asymptotes? So in the first example, in last lecture what we have discussed, we have taken one example and we have calculated the location of that poles whenever k varies. We found that at a particular point, those poles become complex conjugate. That means they just diverge from that real axis. So whenever you start varying that k, after a value of k, you will see that those poles will be complex. That means they will be going away from the real axis. So here, if you have some zeros, open loop zeros, which are infinite zeros, so in that case, this is one of the rules of root locus. That means when k tends to infinity, so in that case, that root locus approaches straight line as asymptotes. So let us just discuss these things through some example, then I think it would be clear. Let us see. So first of all, the statement is the root locus approaches straight line. As asymptotes as the locus approaches infinity. So when that root locus approaches infinity, whenever that open loop plant has some zeros at infinity. So that means here, if we just consider that this is that real axis and this is that imaginary axis, say suppose you have one pole here, another pole here. Just now what we have discussed, that this particular segment would be the part of the root locus. The reason is, if you are here, you can see that on the right you have only one pole, that means odd number. Or on the other way, if you just start coming from this particular side, then you can see that on the right you have odd number of poles, but if you are here, then you can see that you have two. So that means this portion does not belong to the root locus. So this particular portion belongs to the root locus. So now if you start, so what we have seen so far, that means this particular value would be k equal to 0 and k equal to 0, because root locus starts from the pole locations, open loop pole location. So then if you start varying that k, we have seen that when k tends to infinity, those poles will be moving towards that 0, open loop 0. So that means there should be a point somewhere it will go away from the real axis. So now the point is, it may go along that direction, or may go along that direction. We do not know. So it can go in any directions. So just from these asymptotes and centroid, we will be able to say that along which direction it will be going. So let us see. So that means we need to find a point on the real axis which is called that centroid, and from that centroid, basically, so suppose you get say this type of, suppose you get, say this is that centroid. So there is a point on the real axis, and here you have these two asymptotes, and then you can see that, so those poles, so basically will be moving along that line whenever k is tending to infinity. And as I have pointed out, the root locus approaches straight line. So we are actually sketching that root locus because we want to get that qualitative locations of that roots, and when k is tending to infinity, this particular root locus follows that straight line. So now we are just trying to understand what would be the point here. So this point is called that centroid, and how many asymptotes you would have, that we are going to calculate. So there is a formula that is called that real axis intercept, the real axis intercept. So that means this particular point, so which is denoted as sigma, that is that summation of finite poles minus summation of finite zeros. That means if there is an infinite zeros, we are not going to consider, and then the number of finite poles minus number of finite zeros. So this is that formula. And what is that angle of asymptote? So those are, so here if we, for this particular example, you can see that, so those angles are 90 degree or 270 degree, whatever you can say. So what would be that angle? Because if we get that particular point, if we get this particular point, and if we know that angle, so then we can easily draw what would be the asymptotes. So that's why what would be the formula for getting that angle of asymptotes? So angle of asymptotes, that is equal to theta. So that is equal to 2k plus 1 into phi divided by the number of finite poles minus number of finite zeros. So here you can see, and k equal to say 0 plus minus 1 plus minus 2, so on. Here you can see that when these particular asymptotes, the concept of asymptotes comes into the picture, it is clear that it comes into the picture whenever k is tending to infinity and those asymptotes will be going to infinity. That means we are trying to understand at very large value of k, what would be the qualitative locus of the closed loop poles. So it happens whenever there exists some zeros, open loop zeros at infinity. So that means this particular concept would work whenever, so it is needed, so those formulas are needed when some zeros are at infinity. And whenever some zeros are at infinity, so it means, so particular case, if you see this example, that here there is a 0 at infinity, and whenever there is a 0 at infinity, you can see how many finite poles are there, 2. How many finite 0 is there, 1. So there is no possibility of having same number of poles and zeros. So whenever there is same number of poles and zeros, then there is no 0 at infinity. So in that case, the concept of centroid and concept of asymptotes would not come into the picture. That means whenever the number of poles is equal to number of zeros for the open loop system, so then there is no concept of asymptotes and centroid. So that means if you look at this particular formula, so then you can see that number of finite poles and number of finite zeros. So that means this angle of asymptotes would come into the picture whenever number of finite poles is greater than number of finite zeros. That means there are some zeros at infinity. That means this particular definition is well defined. So let us take one simple example and try to understand what is, suppose you have one example, that is g of s equal to k say s plus 2, s plus 4, s plus 6. So this is that open loop. So that is actually k, g of s, h of s. So now we are trying to understand that how many finite poles and zeros are there. So here you can see that so number of finite poles equal to 3. So they are actually -2, -4 and -6. And the number of finite zeros, that is 0. So here this finite. So then what would be sigma? So that sigma, this sigma, here you can see that sigma, this formula is summation of finite poles minus summation of finite zeros divided by number of finite poles minus finite zeros. So what is the summation of finite poles? So summation of finite poles are -2, -4, -6. So -0, there is no finite 0, divided by 3 minus 0. So that is -12 divided by 3, that is equal to -4. So the centroid is at -4. And then what is the angle of asymptotes? So angle of asymptotes is equal to, you can see here, that is 180 degree, k equal to 0 if we take, that is 180 degree divided by 3 minus 0. So that is 180 degree divided by 3 minus 0. So that is 60 degree. And here you can see if you take plus 1, so that is 3 into 60 degree, that is you have 180 degree. And again, if you take k equal to 2, k equal to 2 here, so that would be no, k equal to 0, that is 60 degree, k equal to 2. If we take k equal to 2, that is 5, that is 300 degree. So like that. So here, if we just draw the root locus, that means if we draw that only, draw that root locus, what will you get? That is that real axis, that is imaginary axis, and this plane is S plane. And now we'll first draw that location of that open loop poles, so that at -2, -4 and -6. So at -2, at -4 and at -6. And then you can see that what is that location of that centroid, that is at -4. So this is that point, this is that point of that centroid, and there are 3 asymptotes. Here you can see 60 degree, 180 degree and 30 degree. So asymptotes, one is with angle 60 degree, so this angle is 60 degree, and another angle would be that 180 degree, so this is 180 degree, and that 300 degree is this one. So that is very easy to understand, because we have already discussed that root locus is symmetric with respect to the real axis. So applying this particular rule, that fourth rule, we found this part of that root locus. That means this is that centroid, and there are 3 asymptotes. And if you apply this particular rule, that means rule 3, which part of that real axis are, in the root locus. So here you can see that this portion, that means if you are here on the right, you have only 1, and this particular portion, they are inside that root locus. So just by applying these four rules, we can have that part of root locus. But this is incomplete. The reason is we need to find the other parts. That means whenever k is gradually increasing from 0 to infinity, so at higher value, that means when k tends to infinity, we have seen, that means that root locus would be following that straight line path, the straight line like this. So that direction we have understood, but what happens at which location that closed loop poles would divert from this real axis, that thing we need to calculate. So let us see. So that is rule 5. This is called that real axis breakaway or break-in points. So real axis breakaway or break-in points means here you can see that this particular portion belongs to root locus. So there would be some points somewhere that it will go away from real axis. So we are interested in to find what would be that point. So that point is called that breakaway point. So there is a formula and there is a trick for finding that breakaway point. We know that the characteristic equation is 1 plus k g of s h of s equal to 0. So then we need to write that k equal to 1 by g of s and h of s. Then you take the derivative of that k with respect to s. That means dk by ds. So calculate dk by ds and find the value of s so that dk by ds equal to 0. So that value is actually that breakaway point or break-in point. So let us see, just take one example. So suppose we have one characteristic equation like 1 plus, so this is one example, that is 1 plus k s minus 3 into s minus 5 divided by s plus 1 divided by s plus 2. So if this is that characteristic equation, then as we have discussed now, we need to write that k s minus 3 s minus 5 divided by s plus 1 s plus 2 equal to minus 1, and then what would be k? So that k equal to minus s square plus 3s plus 2 divided by that s square minus 8s plus 15. So then we need to take the derivative of that k with respect to s. So if we take derivative, then what you would get, that is so you all should check this one, divided by s square minus 8s plus 15 whole square. So now at break in or break away point, so dk by ds equal to 0. So what would be that value? So you get one value is minus 1.45 and another value is S2 equal to 3.82. So then you need to check that which point belongs to the root locus. If both of them belong to the root locus, then one of them would be that break away point and other one would be break in point, or they may be both break away point. So that thing we need to check from that root locus. So what we have discussed here, that means whenever a characteristic equation is given, then you write that characteristic equation in that form, k equal to minus of 1 by g of hs. And here we have taken that one example, and we found that dk by ds equal to 0 at break in and break away point, and we get 2 points here, and we need to see whether those 2 points are on the break away point or not. You may ask how to check that one, because if you apply that rule 3, then you can see that which part of the real axis belongs to the root locus, and those break away and break in points, they are actually the real numbers. So just applying that concept, you can easily find which part of that which point belongs to the root locus. From there we can find that which one is that break away or break in point. So what we have discussed today, so we have discussed say 5 rules for sketching that root locus. The first one is the number of branches in the root locus is equal to the number of closed loop poles, and when k equal to 0, so then that root locus starts at open loop poles, and when k tends to infinity, then it ends up at open loop zeros. So at k tends to infinity, when k tends to infinity, the closed loop poles are actually that open loop zeros. The second thing we have discussed, that it is symmetric with respect to real axis, as all the coefficients are real. The third one is very important, that means which part of that real axis belongs to that root locus. And here we have seen that means if there is odd number of poles and zeros to the right, so then that portion of that real axis would be the part of root locus. The fourth one is that centroid and asymptotes. The concept of centroid and asymptotes comes into the picture whenever there are some open loop zeros at infinity. And we have seen how to calculate that open loop, asymptotes and centroids. And the fifth one is that real axis break away and break in points. So here we need to write that characteristic equation in terms of this k equal to something, and then you need to take the derivative with respect to s and then equate to 0, and from there you can find what would be the breakaway and breaking point. So in next lecture I'll be discussing another 2 rules, and after that we will be solving some problems from root locus. Thank you.